Guess we could start the introduction. My name is Professor Onet Mavata. I'm a faculty here in Material Science and Department. And today, we are very delighted to host a dear friend and colleague of mine for a long time. What we're going to do is I will let my postdoc to introduce his bio and who our speaker is. And then our speaker will take the floor from there. But thank you so much for coming.
Thank you, Tim. We have very special guest, Professor Himanshu Mishra from King Abdullah University of Science and Technology, KAUST. He's also a co-founder and chairman at Terraxy LLC. So his talk is going to be on water hydrophobe interfaces, from debunking myths to boosting global food, water, climate resilience. But before going to the talk, I would like to give a very short introduction about the speaker. So Professor Mishra is a scientist entrepreneur at KAUST, working to transform deserts into permanently fertile landscape, advancing global food, water, and climate security. In this talk, basically, Himanshu Mishra shares his team's innovations for transforming arid deserts into basically fertile landscapes, from bio-inspired materials to large-scale field trials advancing food, water, and climate security. Professor Mishra actually earned his PhD in applied physics and materials from Caltech in 2013, followed by a postdoctoral fellowship at UC Santa Barbara. As an Ellings Prize Fellow with late Professor Jacob, he joined KAUST in 2014 as an assistant professor and is now Associate Professor of Environmental Science and Engineering and Associate Faculty at the Sustainable Food Security Center. Over the past decade, his team has raised working to transform deserts into a permanently fertile landscape, advancing global food, water, and climate security. In this talk, basically, Himanshu Mishra shares his team's innovations for transforming arid deserts into basically fertile landscapes, from bio-inspired materials to large-scale field trials advancing food, water, and climate security. Professor Mishra actually earned his PhD in applied physics and materials from Caltech in 2013, followed by a postdoctoral fellowship at UC Santa Barbara. As an Ellings Prize Fellow with late Professor Jacob, he joined KAUST in 2014 as an assistant professor and is now Associate Professor of Environmental Science and Engineering and Associate Faculty at the Sustainable Food Security Center. Over the past decade, his team has raised $7 million plus in funding, in competitive research funding, published over 50 peer-reviewed papers, and mentored a new generation of environmental innovators. His work has been spotlighted by CNN, the World Economic Forum, COP16, and the American Chemical Society.
Well, thank you, Abhishek. Thank you so much, Tim. This is a special talk. And I'll just say very briefly, it's special because my parents, my wife, my parent-in-laws are here, colleagues are here, distinguished MIT scholars are here, colleagues all the way from King Salman Park, even investors are present in the audience. So it's truly a quite a melange of colleagues who have come here. So thank you. A really special moment for me. What I'm going to tell you essentially is a story of our curiosity-driven research over the course of last 10 years. And I'll focus on the translational aspects and leave the debunking part to the later stage if we have any time left. So I will talk more about how to handle the global food, water, climate security thing while creating a very strong business case. Yeah, because as I said, investors are present in the audience. So okay, let's get right to it. Here is the bold question that we ask. And the question is, how do you make deserts forever fertile? Well, it kind of sounds like an oxymoron. I mean, deserts are not supposed to be forever fertile. They're supposed to be tough scenarios. In particular, of course, I'm talking about hot and dry arid regions, such as the Middle East, northwestern part of India, parts of Central Asia, and so on, Arizona, Texas, so on. So soils are predominantly sandy. They don't really hold water or nutrients. It's hot. Water is scarce. So these are very tough constraints. There are additional chemistry constraints, and I'll touch upon them as we go. Yeah? So essentially, how do we do this and also do this sustainably? How do we do this? Yeah? In parallel, as new cities are being created or existing cities are being upgraded in many of these parts of the world, here I'm showing you King Salman Park here. We have esteemed colleagues from King Salman Park also in the audience. This is going to be the largest human-made park in the world. Yeah? Being built in the toughest climate with toughest soil conditions, most scarce water conditions. But still, it is the will of the nation to achieve this. Yeah? So there's a huge pull to create desert rehabilitation and do carbon capture, and also big push to get rid of organic landfills in those desert regions. So while I'm focused in this talk about Saudi Arabia, but the ramifications of what we have done apply to the entire planet, to all the arid regions of the world. Yeah. And of course, there is desire to realize as much as you could sustainably local food security. So food is not entirely imported because of ongoing wars and pandemics, supply chains get stressed. So there's a big desire to also have as much as you could regional food security to also reduce conflicts and so on. And of course, I don't need to tell you, very clever audience, that water as a precious resource, fresh water in deserts, arid regions, by definition, is the most precious resource. It's a very stressed resource. So essentially, when you apply under a hot scenario in desert, when you water a plant, and I'm talking especially of a baby plant, then because plant is so small, it doesn't have much shadow, so most of the water just evaporates. Yeah? Okay. Okay, it should be good now. Now they should hear. Now they should hear. Thank you, Adair. So yeah, most of the water that you apply, it actually evaporates because it's so hot and dry. Wind is dry and sun is hot, so water evaporates. That's obvious. How do you stop it? So what people have done over the years is they put sheets of plastic on wet soil. So you have hectares and hectares of land covered with this plastic sheet. It's supposed to decrease evaporative loss. But the problem is that then we are talking about millions of tons of plastic being landfilled in those regions. It cannot be reused, thin plastic sheets. Yeah? So what do? Well, in our lab, we have been studying insects, nature-inspired flowers and leaves, and studying their secrets. For instance, if you see here, I'm showing you some snippets of some of the rarest insects on the planet. There are around 5.5 million insect species on the planet, of which only 5, truly 1 out of million, only 5 live in the open ocean. And these are these helobaites. And they are super water repellent prototypes. So we studied them, we learned their secrets, and then we apply those insights on how they skate on the water surface. They don't swim, they don't fly. They're under constant attack from birds and fish and so on. And they live in open ocean, with waves and rainfall and so on. Yeah? So we learned their secrets and we translate those insights on technology number 1. This is how we got started in experimenting with plants. When you go to the beach, sand is always wet. We coat sand grains with nanoscale coating of paraffin, and that renders this material into a highly water repellent material. I mean, at the grain level, it is water repellent, but at a macro scale, it is super water repellent. So if you tilt, water rolls off. Yeah. So what do we do with this? Well, let's think about it a bit more. So if sand grains, which are intrinsically wetting, would form some 3-phase contact angle like this. But if I cover this with a water repellent coating, this will change to this. As a result, this curvature shifts to this. So the upshot is, if I put a coating of Sandex or super hydrophobic sand, which we invented, on top of wet soil, it will now, this liquid water will not rise into it. Because to rise, you need a curvature like this. Yeah. So if this water cannot rise until here, then this water does not touch solar radiation. It doesn't get kissed by the wind, the dry wind. So this water would have to evaporate to get out. And water's latent heat is pretty high. So with this approach, you can cut down evaporative loss of water in a desert quite substantially. Yeah. So you apply about 1 centimeter thick layer of this sand, which, by the way, 1,000 kilos of sand requires only 1 kilo of paraffin to be applied, to be rendered into this form. So now the evaporation has been stopped, so the plant can really transpire. And as the plant transpires, it can manage its temperature, it can take nutrients properly, and so on. Yeah. So with this, we boost plants' health, plants' yield quite significantly. Here's the idea again. The mulch prevents the evaporative loss of water, and the wax gets degraded by the soil bacteria over time, and the sand becomes a part of the sandy soil over a course of 1 year. Yeah. So this is how we got started. We did field trials of this. You can see the blue one where significantly higher moisture content in the soil. Oh, what was that? Okay, and then we scale up the technology from producing this material at grams per day scale to producing hundreds of kilos per day scale. We start doing experiments with in fields, and this is how we got started. Yeah, experiments with just to give you an idea. Yeah, here's an idea, because most of the work is done in very large fields, but this is a cool, clean, careful study which shows you. By doing this gravimetry simple mass measurements, we can show we can shut down evaporation quite substantially by applying Sandex on top. Yeah, and so even though the total evapotranspiration from the plant remains the same, but we have significantly arrested the evaporation. What does that mean? It means the plant can transpire much more now, which means plant is healthier, which means plant has much more yield. So, I mean, I don't expect you to read all this, but the yields are significantly higher. Transpiration efficiency is higher. Stomata size are big. Xylem dias are big. And so it's essentially like a little child is going to gym and becoming very strong. Because from the baby child onwards, that plant is used to transpiring much more. So the leaves stomatal sizes are bigger, xylem tissue radii are bigger, and so on. Yeah? And of course, the upshot of all this is yield is significantly higher. Yeah? So this is how we got started back in the day, several years ago. This is our team members applying the material close to the root region. Of course, all is mechanized now. And we got some studies out and took this to the field, and we scaled up the production. So here is a field that we built, our team, our students at KAUST. We created this. This field was built by our team. This is about a hectare in area, 10,000 meters square. Built a pumping station and so on, and scaled the production of Sandex to 1 ton per day. Yeah, but see, water is the primary requirement for growing plants, but water is not everything. Just like humans, water is very important, but you also need food. You need fertilizer, right? So. Oh, and some of you might wonder, how do you apply water if it's all super water repellent? How do you put the water inside? Well, you can do it by leaving a little area right near the dripper where it is dripping water. Here you can leave the normal soil so it can suck water in. So water can go through this hole and spread, right? So this is super water repellent. A little lag. So this area here, this is super water repellent. So water cannot, only vapor can get out, but in the middle, water can go in and so on. Yeah. So this is a small area, but water won't evaporate from the side. So okay, in this first part, we hello. So the other part then is the nutrients, right? Sands are really bad at holding onto water or nutrients. And so when you apply nutrients to the soil, they just get washed down with the irrigation. Yeah, so nutrients just get washed down. Why is that? It's because the negative surface charge density of sand grains is very low. And most of these nutrients like ammonium, calcium, magnesium, manganese, and so on, macro and micronutrients, most of them are positively charged. So they just get washed down. Yeah, and also down. So this is a big problem. So even if you're applying fertilizer, even nitrogen fertilizer like urea, it breaks into ammonium, and ammonium soils are also alkaline. So under alkaline conditions, ammonium becomes ammonia, and ammonia is out of the soil. So the use efficiency is like 20-30%. So what can you do under these circumstances? Here is a snippet of, you can see that sand has much less surface charge density compared to clay, for example. Therefore, some element of clay in the soil is useful. But desert sands don't have it because nanoscopic clay flew away during dust storms because it's nanoscale. Yeah? And then regarding the pH problem is also not just limited to Saudi Arabia or the Middle East. It's actually all the desertified regions of the world. They suffer from alkaline soil pH. So the problems of bioavailability of nutrients, loss of nitrogen fertilizer, and so on, these are global problems. So whatever insights we develop here are translatable to those other soils of the world. Yeah? This I mentioned already, that as a function of pH, ammonium will speciate into ammonia and will go out of the soil. Yeah? And this is about bioavailability, that a lot of the nutrients, even though they are present in the soil, but they are locked. They don't dissolve in water under alkaline conditions, so plants cannot take them. See, they're all getting choked here. Choked, 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 choked. Yeah? So you can have 1000% higher phosphorus in the soil, but still the fruit will show deficiency of phosphorus under alkaline conditions. Serious problem. Yeah? So what can you do? And then I bring this back again because the second technology really couples this gigascale scourge of organic landfilling. And this, by the way, is a shared problem all over the world. Everybody wants to get rid of their organic waste, which is being landfilled, where it rots. It rots and creates greenhouse gases. You don't smell them, you don't see them. Yeah? So about 80% of this carbon will go out as CO2 and 20% as methane. So unless you do methane recovery, you flare it, that methane has a much higher greenhouse gas potential. Yeah? This is a serious problem for climate change. Yeah? So what if there is a way to couple this gigascale pain point of organic landfill pollution and this gigascale opportunity of building cities, building soils? And soils are huge. If you think of kilometer square area and think of amending a meter of the depth, that's a million cubic meter of volume. Million cubic meter. Yeah? Lot of volume. So that is truly the best sink where you want to lock your carbon because of the scale. The scale of the soil is so huge. Yeah? Just to give you an idea, King Salman Park, a 16 kilometer square area with a greening area of about 11 kilometers square, it rises to those, it would require over 100 kiloton of carbon-rich material for soil amendment. And what is that carbon-rich material? I'm going to show you now. Yeah? So what we have done is we have developed Carbosoil. This is a very carbon-rich material. Its key point is it is ultra-stable. You put it in the soil, it lasts for centuries. So we are not building just fertile soils in the desert. We are building permanently fertile soils in the desert. Yeah? This is not a compost. It's not a fertilizer. It's not peat moss. It's an ultra-stable form of carbon. What does it do? It acts as a bottle. It acts as a cup or a reservoir for nutrients. You apply fertilizer, it fills up and it holds them. It doesn't let them leach. You apply water, it holds it. So then plant can take it over time. And its benefits last for centuries. Yeah? So with this, you get significant plant growth, better use efficiency of your resources. And since it is so stable, every ton of this material is equivalent to 2 tons of CO2 captured. Yeah? So those who are interested in carbon credits and so on. How do we make it? Well, here is the full process of making it, and this is our pilot station. We built this pilot station with support from KAUST and from my startup Terraxy. We ran this pilot for over a year, and in this process, we diverted over 400 tons of chicken poop. We love chicken poop. We also love cow poop and green curds and ag waste and so on. But chicken poop is really good because nobody wants it. And it's a pain point for the poultry industry because they have to pay money to landfill it. Yeah? So this material comes and it is subjected to a high temperature process. The technical name is pyrolysis. It's essentially heating it up in the absence of oxygen. When you do that, things will start dehydrating. Yeah, sometimes you toast your bread and you toast it too much, it becomes all charred, right? It's that charring process, but in the absence of oxygen. What happens is then the material significantly dehydrates. Under high temperature, molecules start dancing and they start breaking. They break and they start producing these small molecules. Yeah? And the chemistry starts changing. A significant fraction of single carbon-carbon bonds now become double carbon bonds, aromatize, they become graphitic. Those are very difficult bonds for bacteria to break. That's why this process produces a char which is very stable. You might say, well, what about the energy? Remember I told you these small molecules? These are fuels. As these small molecules are produced and these volatile organics, we shove them in the burner, so the process is self-fueled. That doesn't make sense. Where did the energy come from? Energy came from the sun. As plants grow, they are capturing chemical energy, solar energy and chemical energy. And it's that energy in the chemical bond in the waste which gets utilized during pyrolysis. Yeah? In fact, this extra fire that you see here, this is extra energy we are letting in the atmosphere. This can be utilized to produce renewable electricity. This bio-oil excess can be used towards production of fuel, plastic feedstock, and so on. Now, what is our contribution? What we have done is biochar, what comes out, this ultra-stable material, it is very alkaline in nature. So you cannot apply it directly to alkaline soils of deserts. It kills plants. It's an established fact. What we have done, we have developed a process at scale to convert this biochar into a desert-friendly biochar. So we gave it our trade name called Carbosoil. Yeah, this is our IP, KAUST IP, now licensed to my startup called Terraxy, which I co-founded with a former graduate from my lab, Dr. Adair Gallo. So this is how you deploy it in the soil. You just mix 5% of Carbosoil with the desert sand. That's it. Now that desert sand has the ability to hold on to nutrients and water and utilize fertilizer at high use efficiency, so they grow better. And so right now we are focusing on landscaping sector, high value resorts and construction projects, amazing parks and so on. And there we are disrupting the peat moss market because this is an imported material which has a horrible reputation in terms of greenhouse gas emissions. This material readily degrades in the soil, just like in the landfill, just like the compost, and then it releases minerals which plants take, but the carbon goes out in the air. And this is an imported product. This is premium, expensive product, which is imported. So what if we could replace this with something that is locally made from local waste, prevents landfills, and captures carbon? And the benefits last for centuries, while this peat moss, it degrades within a year. Or even less under the hot conditions of Saudi. If it is hotter, bacteria act even faster. Yeah? So this is the value proposition. So remember I showed you we built this field? Well, we have made some progress. We acquired the land left of it, right of it, and behind it also. So you are looking at around 2,000 native plants, native desert plants being grown under different dosings of Carbosoil, Sandex, under different irrigation regimes, less water, more water, frequent water, less frequent water, and so on. These are 5,000 tomato plants grown under retractable shading nets. So we can open and close the shading net because we want to also ask a question, can we widen the window of planting trees in Saudi Arabia? Is it possible? Yeah? And the answer is yes. Here we are growing 16 different horticultural crops, testing different Carbosoil dosings. and also testing a new generation of fertilizer based on Carbosoil called slow release fertilizers, which we call desert cookies. So these are just some representative results on sensitive plants. This is yields increasing by 40% and so on. These are representative. We have years and years of data on the efficacy of this approach. Of course, you apply it once, then you don't apply after that. You just deal with your plant, and you have accrued benefits year after year after that. I'm going to show you two studies in some detail. So these snippets are not from California. They are from the desert of Saudi Arabia. Yeah? Technology has now been taken from producing gram scales of materials per day to, in our pilot, now producing 1 ton per day. And we have now taken the post-processing part of that technology, which is our IP, to 30 tons per day production. That's industrial scale. So that translates to 6,000 tons per year. It fits beautifully with an industrial scale unit, and I will give you a snippet into that. Yeah? That's where we are heading. Now I'm going to show you some industrial trials with industrial partners who have plans to plant hundreds of millions of trees, up to billions of trees. Yeah? So this trial is done with Aramco, who's also the lead investor in my startup. Yeah? So this experiment was done on the eastern side of the country in a remote place called Khurais, in the middle of desert. Yeah? So here we planted native acacia plants, and this trial was for 2 years. What we found, at this x-axis is 2 years. What we found was, if you see, so here we are looking at trunk diameter. Usually you would think that the height of the tree is the best indicator of growth. Actually, it's the diameter. If the trunk diameter is thicker, it means it's capturing more carbon. Yeah? This is diameter tracked over a function, of course height also, but diameter is a stronger one. And these green ones are Carbosoil treated plants. Note all these plants, all of them get same water, same fertilizer. Yeah? The treated ones got extra only 1 kilo of date palm Carbosoil. That's it, at the beginning of the experiment, that's it. Yeah? And the growth of these is about, and that's a conservative estimate, over 60% higher. 60% higher biomass. How did we find the biomass? Well, we pull out the tree. After 2 years, we pulled them out and we measured their mass and measured soil chemistry and so on. So why was it? How? How do we explain it? Well, when we did soil chemical analysis, we found that Carbosoil treated, all these yellow ones, they just act as reservoirs. Soils that have Carbosoil, they are just much more rich in nutrients, both macro and micronutrients. That's it. And after 2 years, we go and we look at Carbosoil particles. They are beautiful, shiny, fresh particles. Yeah? And they are going to keep doing that benefit for centuries to come. Now see, you are doing carbon capture in this process in 2 ways. One, just the application of Carbosoil to the soil is carbon capture, because otherwise it will be in the landfill emitting greenhouse gases. One. Second, if the plant is growing more, that's more carbon capture. So there's a dual benefit. Yeah? I won't criticize any other carbon capture technology here. Enough said. So this is a summary of that result. So for 3 liters per plant of, in this case, date palm biochar. This is Adair Gallo, our terrific co-founder and CEO. Yeah? This is 1 kilo of date palm Carbosoil. It costs only $1. Now imagine you are applying it to a plant that costs $10,000. A plant, a tree that costs $100,000, which in some great, very high profile landscaping projects, that is the norm. It's a no-brainer. Right? $1 on a $100 plant in airports, in resorts, and so on. Yeah? So the benefit of just this 1 kilo leads to, which is less than 2% of the project cost, leads to 60% enhanced, better, higher survivability, higher growth, higher carbon capture, and so on. Better resource use efficiency also. Yeah? Now, I also am very curious to tell you about this amazing project in the heart of Riyadh, which used to be an old airport. It used to be a site where carbon would be emitted. And now this, being the largest park in the world, is going to become one of the largest carbon sinks. Yeah, very cool, very bold initiative. But see, soils here are very difficult. So for a project of this size, which does not want to deploy peat moss because it's want to be sustainable, how do you build soils of such a project? So it's a perfect ally, perfect test bed for the Carbosoil technology. So we are working closely with King Salman Park. It's a 16-kilometer square area with around 12-kilometer square or so of green area. Yeah. So if you do that times 1 meter of depth, that's 12 million meter cube of soil. Yeah, very large volume of soil. So we have been working with them. The first step, again, with any landscaping project, any contractor, this is the previous was artistic rendition. This is a recent image on site. So a lot of work going on. It's at its infancy. The first step is you want to test it in the nursery. So first thing, we tested in nursery and, oh, this needs coffee. So you can see on the left are Carbosoil treated plants in the nursery, and on the right right is the control, whatever is utilized by the contractor. You can see the benefits, the density of these plants, the volume of these plants compared to these controls. And mind you, the Carbosoil solution is 25% cheaper than the standard mix. And of course, all of these materials, coco peat, compost, they degrade with time. But Carbosoil is there to stay. So its effects are better and it is cheaper. Okay, so the project is interested. Okay, let's go to the field. And so that's what we did. On site, then on land, outdoors, we tested a variety of native plants. And I must emphasize, this experiment was done during the peak hot summer season of Saudi. The conditions under this time, they are very harsh. They are kind of like the harshest conditions anywhere in the world. Yeah. So soils are very difficult, and climate is super, super harsh. This is not the planting season. Trees are not planted at that time, seedlings. Nevertheless, our collaborators and us at King Salman Park, their scientific advisory committee colleagues, they had so much confidence from the nursery result, they said, let's go ahead. And we did. So these are the results. Again, we tested, this is 20-some types of plants. I'm going to show you only representative results. This is Carbosoil being deployed on site. So these are dosing 0%, 2.5% by volume, 5%, 10% by volume, and so on, yeah, in the soil. And so this is mechanized with the regional contractor deployed. And then we are looking at different types of plants, grasses and native plants and non-native plants and their growth. And the results are really, really encouraging. It was started in May. May is, Masha and I left Saudi in May because it was getting too hot. But my brave team stayed there and they ran the experiment and they monitored it. They did a really good job. So these are now, so see, it was planted here, day 0, and this is now month 1.5, 2.5, 3.5. And you can see the growing green coverage. You can see the 0% keeps on struggling because conditions are so hard. Yeah? This is for another plant and another plant and so on. So the benefits in the growth of the plants are quite significant, 50%, 80%, 40% in terms of their either height or their width. In this case, we haven't uprooted them yet. But visually you can see, and by measurements on ground, the results are really compelling. And mind you, these are results under the harshest conditions of Saudi. Usually planting is done in the fall because now the conditions are mild, right? October, November, December until, let's say, March, April. Yeah? But these were done during May, June, July period, harshest conditions. What this tells you is that with technology like, it tells you that with Carbosoil and with adequately applied water, we can significantly broaden the window of planting in Saudi, both for native plants as well as for food crops. Food crops we have even done with radiation management through shading nets, cheap shading nets. And this is a very significant result. And this is for all the plants. These are averages for all the plants. Around 20 different species of plants tested under all the plants show significant benefits under Carbosoil application. All these plants get same water, same fertilizer, same everything. Yeah. One control does not have Carbosoil, but it has compost, and others have Carbosoil on top. Okay. So this was our engagement with King Salman Park. We are also doing work, again, every contractor, first you go with the nursery, you prove yourself, then you go outdoors. Same for Jeddah Airport. Now we are their registered vendor, selling around 6,000 bags of Carbosoil. So it's picking up. And there are other examples. These are some sports pitches, golf course. There are others, and I think I've made the case. Some trials with 50,000 plants, some other project, some other project, some other project. Interesting observation for the scholars. We see this very interesting, this is a three-dimensional plot between the diameter, which is the biomass growth, carbon capture, and utilization of water, irrigation volume. So you can see as the irrigation increases, the biomass increases, and as the Carbosoil volume increases, so as both of them increase, Carbosoil volume and irrigation, there is this parabolic sort of enhancement. If you increase only Carbosoil but not water, it plateaus. It's a very cool observation. So where is this heading? And I guess I will not have time to debunk myths today. We only talk about research translation. So the plan is to take this technology, what we have taken from kilogram to ton to, we are going towards kiloton. The plan is to continue towards megaton and all the way to gigaton. Yeah, of course, that will also mean that this will go beyond Saudi, yeah, beyond Middle East and so on. These are projections for chicken market, poultry market in Saudi Arabia. Saudi wants to increase their food security, so they are increasing their domestic poultry production, which means that domestic is increasing, imports are decreasing, which also means that the waste generation will be higher. Same for cattle and so on. And there are big ambitions to green Riyadh, green Jeddah, because they want to diversify their investments. They want to go into tourism and so on. Yeah? So there is plenty of waste available. This is just a snippet of a poultry farm. So yeah, we are very excited because our first factory is coming up. This is our asset. We already purchased an industrial scale carbonization furnace with the investment we have secured, a pre-seed investment. And now we are raising seed round to build our first industrial scale facility. And it's a rather simple setup with the concrete pad and a shed where this furnace will go. And of course, the furnace is followed by a post-treatment unit, which we have already built and tested at 30 tons per day scale. So the full industrial line of assets are available. Yeah? We just need money in the bank to get going. And we have these big mega scale projects lining up with their demand. And we have this poultry industry which has a pain point to take their feedstock from them. Yeah? So we are setting this factory close to Riyadh. This blue arrow is Riyadh. Green arrow is where we are setting up the factory. And all these red dots, they are all big poultry farms in the area. Yeah? So the biggest in this business model, the biggest cost is transportation. So the plan is to make these decentralized factories which would cater to a big population in Riyadh or other major cities, not a centralized facility. Okay, well, I think, yeah, there is no time left to debunk myths today, but I'll be happy to tell you more about it. I think this is a good point to open up Q&A session. Just very quickly, just so you know that in all the global carbon dioxide removal deliveries in the planet in the very recent past, 90%, and in 24, 86% were delivered by biochar. Yeah? And Carbosoil is the only biochar that works in deserts of the world. That's the value proposition. And we are disrupting the highest value landscaping market where peat moss is the norm, and it's a premium product, yeah, imported product. Globally, this approach is the only approach that can do a giga-scale carbon capture. Why? Let's take a look. I am showing you croplands of the world. See India, super green, Southeast Asia, Amazonia, Brazil, parts of US, and so on. If you just look at the food production, the croplands, they cover about 13% of the land surface. The amount of carbon, let's think about growing plant. You are growing a plant, you're capturing carbon, right? You take the food, now the plant dies, it releases carbon. Next year you grow carbon again, you grow plant again, take food, plant dies. There's a cycle that's going on. This cycle cycles about same amount of carbon, about 10 billion tons of carbon per year. This is same amount of emissions from all other human activities. Let it sink in. So if we can break this cycle, because see, food security is non-negotiable. We all love our food. But if we can break this cycle by locking that ag residue in the soil, by making a compelling business case out of it, that's how we can create very strong business, a global business, and mitigate climate change. And the sheer size of ag footprint renders it to be the only method that can do this dent on this problem, the scale. Okay, with this, I want to acknowledge my co-founder, Adair Gallo. He's just a rock star, very lucky to work with him. We've been working together now for over a decade. And yeah, and the team, we have Batul Albar, she's a student in the group, serves as general manager, full-time, team members, our advisors, and you. Thank you.
Great. Now the floor is open for questions. Anyone with questions for speaker?
And keep an eye on the online also, if somebody has questions.
Yeah, I think this is very exciting talk, very eye-opening. I have like two questions. My first question is, you said for soil X or sand X, and even for carbochar, you put for sand X, you put like 5%, some layer thickness.
1 centimeter thick.
1 centimeter, and for for other, you put some amount volume percent, like 5%, 10%.
Yep.
How do you determine how much is enough, or what is the optimum to see the final performance? Or
oh yeah, that's a very good question. Yeah, so we did for Sandax and Carbosoil both. One goes on top, one goes in the soil. So we apply different dosings and look at the plant growth, effect on plant growth. We can also do a pot study for water loss, and we can see if I put a 5 centimeter thick Sandax, no water will get out, but then it's not cost effective. Same for Carbosoil. So once you can, Carbosoil is so great. I am a little bit biased. So let me step back. Let's say you are in desert and you say, I want to build a great soil, right? So, but you cannot apply peat moss because you want to be sustainable. What's your option? Compost, right? So there are purchase orders that run into millions of tons of compost in these mega scale projects. Now see, okay, so you have compost. Let's apply compost. So let's say you apply 25% compost by volume because you want to increase carbon content. But compost itself has enough salinity that first you apply that. Soil is alkaline to begin with. Now you apply something else to it which has high salinity. It's toxic to plants. So you're limited. Carbosoil, on the other hand, is an engineered, it's a tailored material. You can take its salinity pH wherever you want. So you can, in principle, grow in 75% by volume carbosoil. Of course, the economics may not add up, but for nurseries, it's still a viable option. When you have a small seedling of something high value, and then this carbon ball goes in the soil, so you get carbon credits for it. Yeah. So the dose is a function of benefits and cost.
yeah. So my follow-up question, like these studies with plants take 6 months to even 2 years, depending on the plant nature. How do you optimize the process from lab to industrial scale where you need to test some composition beforehand before even waiting for 2 years or something to see the final result?
Great question. Rapid iteration. You don't wait for perfection. You go fast. And my co-founder is really good at it. Yeah. Yeah.
Okay, my final question.
Yeah.
My final question is that you said that this carbochar acts as a
Sponge.
store or something to
Yeah.
hold these.
Yeah.
Do you have some visualization of that or some video or microscopic mechanism how actually?
Oh, yeah. Absolutely, absolutely. So it's a material, imagine acetic acid, right? If you put acetic acid in water and pH is 7, it will be acetate, right? If the pH is above the pKa of this weak acid, it will be fully deprotonated. So this carbosoil has got several carboxylate groups and also pyridinium groups. So under pH, soil pH, which is 8, 8.5 in Saudi region, which is alkaline, all the carboxylate light up. All the acids are now carboxylate. So it's in moist conditions, it's essentially a negatively charged material with some hotspots of pyridinium, which are positively charged. So in a loose terms, it's a bit of a zwitterionic material, which is very inert. So when you apply fertilizers, these are plus minus things, they come and they attach. It's just pure electrostatics. And recently, we have also figured out how to boost this cation exchange capacity by 200%, 300% through a simple process. So we can tailor that also. So we can tailor nutrient holding capacity, salinity, pH. So it's an engineered tailored material, tailored for alkaline soils of the world. So with this, we have unlocked the potential of biochar for alkaline soils of the world. Let me make one more comment about acidic soils of the world, right? Just so you can appreciate the impact. As I showed you, biochar delivered 90% of the deliveries of carbon credits. I didn't do it. World is doing it, right? All of those are done. All that research is concentrated in the acidic soils of the world. Look at where you are. Look at Australia, parts of Australia, parts of Europe, Brazil, where the original biochar applied soils were discovered, acidic soils. Why? Because biochar is alkaline, super alkaline. You put it in acidic soils, they neutralize each other. It has a beneficial effect. But if you put it in alkaline conditions, it's a disaster. So we have unlocked the potential of biochar for the blue regions of the world. And there is a tremendous value to be created. Yep. Yep.
Great. Any other questions?
I'd like to add a comment. I had the privilege for 10 years of working at King Salman Park, which Dr. Himanshu was referencing. And he noted, but I really want to impress a couple of points on this, because this is really revolutionary. Places like Saudi Arabia, call them the purple blue zones, most of those were under the ocean for millions of years. So we're talking sand, compacted and with a lot of salt. So it seems unlikely that you could ever grow a forest in that kind of condition. So King Salman Park's trying to do this, and there are challenges. We meet this amazing lab that has solved for the remarkable notion of salinity, which is our killer. It kills in these former marine environments. And we had an unusual and bad circumstance that I think is going to change science. It takes a while to get big programs to approve things, and waiting. Spring goes by, so we're left with trying this trial this summer, she said, where, forget dormancy, everything dies. And the rock star science of Dr. Himanshu and Dr. Adair and all this disrupts the entire possibility set. I really want to emphasize this for the world, for all these arid areas, the purple areas, that you could grow. You could have a whole nother growth season. And these are all countries that have very little water, except Saudi Arabia, don't have a lot of money for food. You just added a whole season when everything's supposed to die, and they did this. So we went to King Salman Park and said, leaving this on the other side, said, it all dies, no one will criticize me. Of course, everything dies. And it was the opposite. this is a major global breakthrough, and I really want
Yeah,
to
see,
emphasize.
they don't germinate here, 0%. This soil has compost.
It remains zero. Everything
Right?
is zero.
Look at this.
Yeah, and
This is
a
on
matter
site.
of, yeah, just a few.
Under quite harsh conditions. Like, I did not believe this was going to work. So we were prepared to redo the whole operation starting October.
Right.
But then
So
Anne
we
and
do
her,
this
yeah.
at like 5 or 6 in the morning of planting. After 6:30, you can't be out there. I mean, you will be wiped out as the plants are. So this is big, and it's, you know, just an amazing thing that they have done. And I think you will watch this evolve and change the food possibility set for poor arid climate countries.
Fascinating. Fascinating. Thanks so much for the comment. Thank you.
Thank you.
Anyone from Zoom? Any questions on the chat? We can ask them. Anyone from the Zoom? Do you have any questions? I guess maybe I'll add a question or two to you. I guess maybe I missed this. Compared to other biochars, I'm curious if you could comment on the chemistry of your biochar in terms of its different composition to the extent you can share.
Yeah.
Yeah.
So the biggest is the alkalinity. Think about it. The food that we eat has got significant amounts of potassiums. Actually, you can even make biochar out of living systems, plants, and if poultry gets infected and the whole bunch of birds die, anything living, right? This humans. Anyway, so we all have got potassium and calcium and magnesium and these things in us, and the carbon-based matrix, right? So when you carbonize this thing, it undergoes massive dehydration, so significant water thing gets out. Carbon matrix undergoes, half of the carbon goes out as CO2 in the process, half carbon gets locked as biochar, and all these ions, so potassiums and calcium, they don't evaporate, so they all get concentrated. So and they are all alkaline earth metals, so that's why it's hyperalkaline. It also depends on temperature that you cook and so on. So it's not like it's mercury or cadmium. So if you even remove them, the removed soup has beneficial quality for fertilizer, to be a fertilizer on dilution. So yeah, we just bring those parameters down.
Yeah. Another question is, you mentioned about the 100 years of stability. I'm curious what type of accelerated testing is commonly done to suppress this or to accelerate the aging of such biochars.
Yeah, so the earliest findings were in soils like terra preta, where about 30 years ago or so, scholars like Stephen Joseph, Johannes Lehmann at Cornell, they found these, they started looking into those soils. Those are acidic soils, they are under different conditions, but still they have significant amount of stored carbon, and through carbon dating, they deduced that they were at least quite significantly old, 1500 to 2000 years old. That's how this whole thing started in the 90s. So now biochar has been studied so much that we know more about biochar than about soils. So biochar's half-life is determined on the basis of its hydrogen to organic carbon ratio or oxygen to organic carbon ratio. Yeah? And this is the graphitic content. So if you think of, let's say, glucose, yeah? So plants will make glucose, capture CO2, water, you make glucose. So it is C6H12O6, right? So if you make a ratio, it is CH2O, right? So the ratio of H is to C is 2. Ratio of C, O to C is 1:1, right? Okay, can I write somewhere? Here. So C6H12O6, which means that my hydrogen to carbon ratio is 2 and my oxygen to carbon ratio is 1. Yeah? When you do when you convert biomass into biochar, this ratio would drop, let's say, to 0.5, 0.6. This ratio would drop also quite significantly, 0.3 or something. And this is an indicator of graphitization in the matrix. So the lower are these ratios, the more stable it is. And it's a function of temperature. If you do pyrolysis at a low temperature, most of the stuff that comes out, it has a more water-soluble content and it's easily degradable. If you do pyrolysis at around 500 degrees Celsius, then kind of irrespective of the biomass, plant mass, ag residue, cow manure, animal manure, and so on, the material you generate is quite high stability. If you go even higher, 900 degrees Celsius, then you will end up producing mostly oils, bio oils. Yeah.
Thank you. So I think we don't have time for more questions unless there's urgent question in the chat. No urgent question in the room? If not, let's thank our speaker.
Well, thank you.